My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 243rd International Physics webinar, and we'd like to welcome you all to a joint session between our Department of Physics, Pabna, University of Science and Technology, and the Institute of Theoretical Physics, Utrecht University, Netherlands, Europe. And we have with us here today Dr. Elisa Chisari, Madam, Assistant Professor, Institute for Theoretical Physics at Utrecht University, Netherlands. And she has already connected with us, so I'd like to welcome our speaker. Madam, good afternoon and good evening to here. So thanks for accepting our invitation. So before going to you, I'd like to welcome our audience and inform them that the title of our today's international webinar is the Understanding Cosmology with Galaxy Shapes. Very exciting topic. I think you will enjoy it, and you can join with us directly using this link. I will give this link in the comment section. Please check it, and you can also ask question by commenting. So please enjoy it and stay with us. So, madam, it's your time. You can start your session.
Okay, thank you very much for the invitation.
It's my pleasure.
So today I'm going to talk about understanding cosmology with galaxy shapes. So we're talking about understanding the composition and evolution of the universe through the data that is accessible to us. And some of this data is the shapes of galaxies. So we'll see how that comes into play. The outline for this talk, we're going to be talking about what are the open questions when you think about the composition and evolution of the universe today. What do we know? What don't we know? And how can we use the shapes of galaxies to understand, find answers to these open questions? And when I talk about the shapes of galaxies, we'll be talking about two phenomena. One of them is gravitational lensing, and the other one is intrinsic alignments of galaxies. And I'll say what these are and how they can help us in the future to answer these open questions. So here's a timeline of our universe. We think that our universe started with a Big Bang, and since then the universe has been expanding. As the universe expanded and cooled down, the gas that was present in the universe very early on turned into stars and galaxies that we see today. So that's us on the right of this picture, observing the universe. And this is the time of the Big Bang, and the universe, as I said, cooled down and expanded and formed the galaxies that we see today. There are many open questions about the evolution of the universe. We don't know exactly what physical processes drove this early expansion period that we call inflation. We don't know much about the current expansion of the universe. We think that it's driven by a force that we call dark energy, but we don't know much about that. And there are other questions that I'll come to in a second. Now, to try to understand the universe, we have to be able to measure something from it. And here in this picture, you see two types of measurements that are currently used to study cosmology. So the first one is the light that the oldest light that we have access to. So this light comes from an epoch when the universe was about 400,000 years old. And this light has been traveling since then towards our telescopes, and we still observe it today. So it's a very low temperature background, which nevertheless we can still measure today. And this is what we call the cosmic microwave background. And the other light that we have access to that we can measure with our telescopes is the light coming from galaxies. So if we map the positions and the shapes of galaxies, we can also probe the current universe, the current expansion epoch of the universe. So we have access to this information very early on and also very late, and we can try to extract information about the universe from these observations. So what are the questions that we're trying to address in cosmology today? We want to know what is the origin, the composition, and the evolution of our universe to better understand our place in it. As I said, one of the main observables that we have access to today is this light, this old light that is coming from a baby universe, a universe that was 400,000 years old. And this is the furthest back that we can probe in the history of the universe, at least for now. So this map that you're seeing in this picture represents a map of the whole sky, and the colors represent changes in the temperature of this light. So in some regions, the temperature is hotter, and in some regions, the temperature is cooler. And it looks like noise, but it is not. There are actually patterns encoded in this map that can help us test our models of the universe. So in general, what one measures through these maps is the temperature here and the temperature here, for example, so just in 2 points separated by some distance, and we find the relation between these two temperatures. And then we plot that relation, which is shown here in the red points from the Planck satellite. And we test our models, so we have models for how this relation should behave, depending on how the universe started, what the universe is made of, how it has been evolving. And you see that that model, which is the blue line, goes through the data really exquisitely. So the data has tiny, tiny error bars, which you can barely see in these points, and the line goes through it very, very well. So it means that our model for this baby universe is very good. So what do we learn about the universe from making this comparison of the data and the model? We learn that our universe is made of only 5% matter that we can see and touch, which we call ordinary or baryonic matter. So that's this symbol over here. We know that the universe is made up of 27%, something that we call dark matter. So we think that this is additional matter that makes gravity stronger, but we don't know what kind of matter this is. It's not matter that interacts with light, so we can't just shine a torch on it and see where this matter is. It's dark matter, so we can't see it. And then 68% of the universe is in the form of dark energy. So this energy, we think, is responsible for driving the expansion of the universe, the accelerated expansion of the universe today. But again, we don't know very much about its origins. So we have a lot of open questions here, despite our models for the universe being very good. The questions are, what are these dark components, this dark matter, and this dark energy? And we're still looking for answers to these questions. So for this talk, I'll mostly be talking about how we look for answers to the question of what is dark energy? Why is the universe again accelerating its expansion in a new phase? And there are many options for what this dark energy might be. So in Einstein's theory, it could be something called a cosmological constant, so just a constant that you add to Einstein's equations, which is allowed by the theory. And it's some extra form of energy that is simply there, it doesn't change with time. It could also be some kind of fluid that is everywhere in the universe. And this fluid has some equation of state, which is the relation between the pressure and the density of the fluid. And we parameterize that equation of state with this parameter W. So if this W is -1, then that fluid is equivalent to a cosmological constant. Or it could be that the reason that we have what we call dark energy, or the accelerated expansion of the universe today, is that Einstein theory needs some modifications. That is not the end of the story. So we don't know which one of these options is the correct one. And what we're trying to do nowadays is to build experiments that will tackle these different possibilities. In general, when we talk about the cosmological model, we encapsulate it in different parameters, and I've already introduced some of them. So the amount of baryonic matter in the universe, the amount of dark matter in the universe, the amount of dark energy in the universe. In addition to that, we have this parameter W, which is the one that parameterizes the equation of state of dark energy. And you will also see this other parameter S8, which I'll explain in a moment what it is about. But essentially, you have to think of these cosmological experiments as experiments that try to quantify what are the values of these parameters. And this is what's going to tell us something about our models for the universe. Now, we've used this cosmic microwave background a lot to try to understand the physics of our universe. But if we want to have access to this information about dark energy, we really need to probe the current epoch of the universe. And for that, we need to map the galaxies, as I already mentioned. So now, in comparison to what you were seeing before, this is, again, a map of the sky, so the full sky that is observable above us. And in this map, every point is a galaxy. So now we're no longer looking at this light from the early times of the universe. Now we're looking at galaxies, so an epoch much closer to the epoch where we live. Each point here is one galaxy, and the galaxies that are painted in blue are galaxies that are closer to us, and the galaxies that are painted in red are galaxies that are very far away from us. And in the same way that we studied the temperature patterns in the cosmic microwave background, with the galaxies, we can also look for patterns in these maps. And the type of patterns that we look for are patterns that relate the positions of the galaxy. For example, we ask, are there more galaxies here? And how does this number relate to the number of galaxies over here? Similarly, we do the same with shapes. We ask the question, is the shape of these galaxies over here related to the shapes of these galaxies over there? And there are connections, and we'll see what those connections are. So what is the role of galaxy shapes in testing our models of the universe? So let's see why they give us some information. So imagine that you're an observer here on Earth, and you're looking at a very distant galaxy that I labeled gamma over here. The light from this galaxy is coming towards our telescopes through some path. Now, normally, that path would be a straight line. But when the light encounters some gravity in between, like the one generated by this very massive galaxy over here, then that path is no longer going to be straight. The light is going to be deflected, and it's going to come through this curved path that we called a geodesic. And this is a prediction of general relativity. So the fact that this light is coming through this curved path means that the shape that we observe for the galaxy is not the original one, because the photons seem to be coming from a different direction. So instead of coming from here, from a straight line, they seem to be coming from a slightly different direction, like here. So that means that the shape of the galaxy is going to be distorted. This is what we call a gravitational lensing. And this gravitational lensing can encode information about the cosmological model parameters. The reason for that is that depending on how much matter you have between distant galaxies and ourselves that is causing this gravitational potential, you're going to have more or less lensing. So the amount of matter, the total amount of matter, omega matter, changes this gravitational lensing effect on the galaxies. Also, depending on how strong the potential is, so not only how much matter you have, but also how clamped it is by gravity, that is also going to change the gravitational lensing, and that's this parameter S8. But there's more. How much lensing you have depends on these relative distances that I marked in orange between us, this lens, and the lens and the background galaxy. And these distances depend on the expansion rate of the universe. So they depend on dark energy, so on this little W parameter. So the bottom line is that lensing contains information about all these cosmological parameters, and so it's a useful measurement to make, because then you can contrast your models for the universe to your measurements and learn something about these parameters. Now, in practice, it's not like we have only one lens in the universe, but we have very many of them. So imagine that, again, we're an observer here on Earth, and we're looking at a very distant galaxy over here. The light that comes from this galaxy has to travel through the whole structure of the universe to get to our telescopes. And along the way, it will encounter multiple lenses. So all of this structure that you see here in purple is the matter in the universe that is clumping due to gravity, and it is this matter that will cause the lensing of all galaxies. So I can go and measure the shape of a galaxy with my telescopes, and I will know that it's going to have distortions that come from all these lenses that are along the way. So similarly, this is just an example for this one distant galaxy, but in practice, because this gravitational lensing effect is tiny, we need to have a lot of galaxies to be able to measure it accurately. So then we make big maps of the sky where we measure millions of galaxy shapes, and each one of these galaxy shapes will have these small distortions that will be caused by all the lenses that are in front of them and through which the light has to travel in order to get to our telescopes. By looking at galaxies that live in different epochs, we can answer the question of how has the universe been expanding between these different epochs. So if I measure gravitational lensing here, and then I measure the gravitational lensing here, and then here, then I have 3 data points, one per epoch of the universe, and epoch we normally label with this quantity called the redshift. So I have one measurement of how much gravitational lensing there is per epoch of the universe, and this way I can see how much it has been expanding, and that connects directly to my models for dark energy. So what does this look like in practice? So here is an example from an actual telescope observation of a very extreme lensing event. So the lens here are all these yellowish galaxies that you see in this image. And the objects which are being distorted, which are in the background, so behind these yellow galaxies, are the ones which have been turned into arcs. So you see, for example, this arc over here, this one over here, these ones over here. All of these arcs originally were simple galaxies. But these simple galaxies, because the light has gone through these lenses, they have been distorted into these arc-like patterns. When this happens, we're talking about a case of a strong gravitational lensing. So you can have these distortions into arcs, sometimes rings, sometimes you have multiple images of the same object, and that's called strong gravitational lensing. I work more in the regime of what we call weak gravitational lensing. In weak gravitational lensing, we assume that every single galaxy in the universe has been gravitationally lensed, even if a little bit. And by measuring a lot of them, so if I collect enough of them, I should be able to recover these gravitational lensing patterns. The trick to doing that is knowing that gravitational lensing is coherent. So that means if I have a region of the universe that has a lot of matter, like this one over here, and I label the density contrast in that region delta, then that clump of matter is going to distort every single galaxy in the background, at least a little bit, by making it a little bit more elongated around that matter over density. So if we measure enough galaxies we can try to discover these patterns in the data. And the level of precision that we're talking about is that the shapes deviate from the original one. So the axis ratio of these ellipses deviates from the original one by about 1%. So it's very small, and that's why we need a lot of galaxies. So thousands, millions nowadays in current campaigns, billions in campaigns that are starting just in over a couple of years. How do we measure these patterns? Well, we make catalogs of every galaxy that we can see in the sky. And for each galaxy, we measure the axis ratios and orientations of the ellipse, that is the galaxy. So each galaxy will be a collection of stars. And from those stars, we can look at how they're distributed and model them as an ellipse and find the axis ratio of that ellipse and the orientation of that ellipse. And that's what I called EI for this galaxy I and EJ for this other galaxy EJ. And these galaxies are separated on the sky by an angle that I call theta. So then the patterns that we're looking for are relations between these two shapes of the galaxy. So we're asking the questions, are two galaxies that are next to each other, for example, are their shapes connected? And the reason for doing that is that if we go back to this image, right, we can see that the shape of this galaxy is going to be connected to the shape of this galaxy. Why? Because both of them are being deflected by that same density contrast. So their orientation is related to one another. So that's what we're looking for. So effectively what we do is we take these catalogs of galaxy shapes and then we make a plot of this quantity called the correlation function, where we sum over all the galaxies that are there in our catalog and we multiply two ellipticities together. So I multiply this one by this one and sum over all the pairs of galaxies that I see in my catalog, and then I make a plot of this quantity. So if the galaxies are very close in the sky, so they're very separated by a very small angle, then the two shapes will be related. If I go to galaxies that are separated by larger distances in the sky, the relation between their shapes will be less because they're very far apart, so it's unlikely that they're going to be lensed by the same objects. Okay, so this is what we measure. And then what we do is we take our models for the universe with the parameters that I just presented before, and we fit this data with some line. And from doing this, we can find what are the best parameters that fit this data, best fit model of our universe. So we end up with results that constrain the values of these cosmological parameters. So for example, one could take any combination of this. So a common one is S8 and omega matter. And so you would see here constraints on one parameter, constraints on the other parameter, and 1, 2, and 3 sigma confidence areas. So I'll show you an example of that. Let's take a look at the real data, what it looks like. So this is data from the kilodegree survey, a survey of the sky that was carried in the European Southern Observatory VISTA survey telescope, the VLT survey telescope. And what this observatory did was stare at the sky for many years and make a map of, as I said, millions of galaxies. And for each galaxy, we would measure a shape. And these shapes, as I said, are connected. So if I try to measure how connected the shapes of galaxies are, so through the correlation function sigma plus, and then as a function of separation between the galaxies, so that's theta, I get plots that look like this. So all the circles are actual data from the telescope, and the lines are different versions of a model that we have for this data. These numbers, 1, 1, 1, 2, 1, 3, 1, 4, so 1, 2, 3, 4, they indicate different epochs of the universe. So 1 means very close to us, and 4 means very far away from us. So what we're trying to do here is we're measuring how much gravitational lensing do I have in different epochs of the universe. So today versus back in time. And we're trying to compare the model to these data points. And you see that the model goes through the data points very well. And then from this fit, we try to infer what are the values of the cosmological parameters. So here's an example of that. So from that data that I just showed you, you can constrain how much matter there is in the universe today, and what is the amplitude of the fluctuations in the density field today. So these are both part of that cosmological model. So these are quantities that are in our cosmological model that we want to constrain. And you see that we obtained, so for example, you can look at this pink contour over here. So these are the results from the gravitational lensing. So this is the 1 sigma, so 68% confidence level contour of what the values of these quantities are in our universe. We can compare that to the results from other experiments. And for example, this orange contour, this comes from a measurement made on that cosmic microwave background that I spoke about before. So this is a measurement made very early on in the history of the universe, and this is a measurement that we make at later times, at times that are closer to our own epoch. And you see that there is a small difference between this pink one and the orange one in that they don't fully overlap. So if the universe were a cosmological constant, if dark energy were a cosmological constant, we would actually expect these two to fall on top of each other. Now, this could be a hint that we need to go beyond that cosmological constant model and try to see if there's something else in the universe that is causing this difference between the two experiments. The difference is not so big for now, so it's a bit early to say whether a different model for dark energy is needed. But this is something that the future telescopes will be testing once again to see if they can reproduce this result and to see if this indeed shows tension between the early universe and the late universe. So again, we don't know yet, but it's an interesting question to ask and something that it's currently being explored with a lot of attention. Some possibilities are that indeed maybe the cosmological constant is not a good model for the universe, and then you need some kind of fluid, like I said before, and that would actually help resolve these tensions. It could be that you need, for example, some kind of dark energy that happens early on in the history of the universe, that's called early dark energy, so that could also help relieve these tensions. This tension that I was just showing you, it's not only present in the gravitational lensing data, we also see from other data sets that the early universe behaves slightly differently than the late universe. So there's a little bit of a puzzle there. Why is it that the current expansion rate of the universe, if we focus on objects that are close to us, seems to be a little bit faster than if we extrapolate the one from the early universe? So there is some puzzle there that still needs to be resolved. So this is one of the exciting things that's going on in the field of cosmology. To solve these tensions, we need more data. So this is one of the experiments that is coming up in 2023. This is a picture of the Rubin Observatory, and it's being built in Chile. And it's going to measure billions of galaxy shapes over half of the sky and during 10 years of operations. So we're looking forward to the beginning of this survey because it will bring a lot of new data on gravitational lensing and also on other probes of the universe that we can use to solve this mystery of dark energy. Okay, so now let me talk about another phenomenon that changes the shapes of galaxies, another physical phenomenon that affects the shapes of galaxies, and why we could perhaps also use it in understanding cosmology. So this is a little bit more experimental. So it's not a probe that is currently used, but let me try to convince you that it's also a promising phenomenon that perhaps can help us in addressing some of these questions. So let's start with remembering that in the universe, there are roughly two types of galaxies. This is a simple picture, but roughly, let's say, there are two types of galaxies. There are galaxies that look like disks, like the one on the left. They're normally blue because they're forming a lot of stars. Or Milky Way is one example of a galaxy like this. And these galaxies have a very well-defined plane of rotation, so the motion of the stars is very orderly. They have some angular momentum, and this angular momentum can be torqued by other galaxies, and it can make the galaxy, the disk of the galaxy, flip. Then we have the elliptical galaxies. Elliptical galaxies are redder, like you see in this picture. They are older galaxies, so they're red because they don't have that much gas anymore, and stars are not forming anymore. So when stars are forming, you have blue galaxies, but when you stop forming stars, the populations of stars that prevail are those that are old and red. So those are called elliptical galaxies as well because of the shape of the galaxy. So there's no longer a disk, so there's no orderly rotations. The stars are orbiting in different planes, and this gives a galaxy an elliptical shape, like a little bit like an egg, for example. Now, we think that the orientations of these galaxies, both the disks and the ellipticals, change across the universe due to different phenomena. So, for example, we think that the disks that have this angular momentum, as I said, can be torqued and can be flipped, can swing from side to side because of these torques by other matter or other galaxies. For the ellipticals, we think that there's something else that's going on, which is that if you have an elliptical galaxy with an X shape, then the galaxies that are nearby will be pulling and pushing from this elliptical galaxy and will make it a stretch in particular directions. The other thing that can happen to these galaxies is that they accrete other galaxies. So sometimes they merge with other galaxies. And they do so from preferential directions. So it's more likely that they will merge in the direction where you see many galaxies than in a direction where you see very little matter. So this can also change the shape of these elliptical galaxies. For the rest of this talk, I'm going to discuss mostly the elliptical galaxies because for the disks, there's very little evidence of this torquing phenomenon. We think that it exists. We see it in simulations of the universe. But so far, the observations are scarce, so I won't focus on them. I will focus mostly on the ellipticals, which we know more about right now. So this is a simulation of the universe where all the white points correspond to the distribution of matter, so there are matter particles in this simulation. Just to give you an idea, the distance, or if you think about the nearest large galaxy to our own, this is the Andromeda galaxy. So this is roughly 100 times the width of this simulation box. It's about 100 times the distance to that Andromeda galaxy. Just to give you an idea of the scales here. Each ellipse that you see here is a very massive elliptical galaxy in the simulation. And these elliptical galaxies have a shape. So what I've done here is I represented the shapes with an ellipse. So for every galaxy, I look at how the stars are distributed. And then I calculate the inertia tensor of these galaxies, and that gives me a shape, so an ellipse that represents the galaxy. So from that ellipse, I have an orientation and I have an axis ratio. Now you can see even by eye that these ellipses are not really randomly oriented in the simulation. So let's focus maybe, this one is a nice example here at the top right of the screen. So here we see a galaxy whose major axis, this axis, is pointing in the direction of all these other galaxies. This one as well, right? So the major axis is pointing in the direction of these other galaxies. And the same happens throughout the simulation. So you can look at other regions, for example, here, or maybe here, it's very clear that this galaxy is pointing in the direction of all these other galaxies. So this is what we call the intrinsic alignments of galaxies. And as I said before, we think that the reason for this phenomenon is the tidal field of the universe. So we think that the same gravitational tides that make the oceans rise on Earth are responsible for making the galaxies change their shape. So that's because if you have two regions of high density of matter, like this one and this one, these two regions will pull from a galaxy that is in between and will make it stretch along that particular direction. And we think that that is the reason why we see, for example, this galaxy pointing towards that one over here. This phenomenon has been observed again with maps of the sky. So this is an example of such an observation, just to show you that this is present in the real data as well. And what we're seeing here is a survey of a lot of these red elliptical galaxies, like this one that you see here. And these red elliptical galaxies, their shapes have been measured, and the question asked was, do these galaxies point towards each other? And that's what this quantity in the y-axis represents, is the correlation between the shape of a galaxy, labeled plus, and the position of other galaxies, labeled g. So how much one galaxy points towards the location of other galaxies. And this is plotted as a function of separation between galaxies. So these are galaxies that are very close to each other, and then these are galaxies that are very far away from each other. So what we see in this picture is that all these red points, which correspond to the data, are significantly above zero. So we're seeing a non-zero value for this quantity. And this indeed represents that the galaxies point towards each other. And they do so very strongly because these error bars that you can see in this plot are really tiny, are very small. The different lines that you see in the plot represent models for this alignment of the galaxies. And we see that some models work better than others. So the one in blue, which is called the linear alignment model, and I'll say a little bit more about that soon. So that one fits the data pretty well. And then there are extensions of that model. So when you go to smaller separations between the galaxies are more aligned than the model predicts. So all the red points are above the blue curve. And you need extensions of that linear model to try to explain their alignment. Now we will mostly focus on this regime for what remains at the top. So we'll focus on the alignments of galaxies across large scales and this linear alignment model that works very well. So in this linear regime, the model assumes that the intrinsic shape of a galaxy, which I called I, is proportional to the projected tidal field of matter in the universe. So this is the gravitational potential of all the matter in the universe. And these operators, which are quadratic derivatives in the x and y direction, they represent changes in the gravitational potential in different regions of the universe. So essentially what this model is telling us is that the stretching of the shape of a galaxy is proportional to the changes in gravity from one side to the other. So this is what we call the tidal field, right? The changes in the gravitational acceleration vector. So why is this model and this observation interesting to cosmology? Well, let's recap some of the open questions. So I'm just going to give you one example of this, of how this could be used. So remember that we said that the universe had two accelerated expansion phases, one that started very early on, which we called inflation, so right after the Big Bang, and the other one that we call dark energy, well, it's the expansion that we see today, and we think it's driven by dark energy. So why would one study these alignments between galaxies? Well, just to give you one example of a possible application, one that hasn't been realized yet, but which we have proposed in theory, is that depending on the physical processes that drove this inflationary period of the universe early on, there will be imprints that are left over in the alignments of the galaxies. So the idea is that depending on what fields or what type of matter, what type of energy was driving this accelerated expansion early on in the history of the universe, that will change the tidal field slightly early on and will leave an imprint on the alignments of the galaxies. So I change gravity early on, I leave some clues of these in how the galaxies align today. So this is something that we proposed a few years ago, which has now been validated in simulations of the universe. And here what I'm showing you is that depending on the models that you have for this inflationary period, you can get different alignment strengths for the galaxies. So these are all potential models for the early universe. So 1, 2, 3, 4, 5, 6 different models. This is just a toy example. You could have more. And this is the separation between the galaxies. But now, these are galaxies that are very close together. And these are galaxies that are very far from each other. So depending on these models for the expansion of the universe early on, we can change how the galaxies aligned on the larger scales especially. So these curves tend to constant when the galaxies are very close together. So that means that there's very little change on galaxies that are very close together. But when you look at the relation between the shapes of galaxies when they're separated by very large distances, that's when you see a difference. So this is something that one could potentially test if one measured the shapes of galaxies in a survey like a Rubin Observatory. This is something that one could potentially test with those measurements. So to conclude, I think galaxy shapes have many different applications to cosmology. So we talked about gravitational lensing, and we talked about intrinsic alignments. Some of them we're currently realizing, like the gravitational lensing. Now it's regularly measured and modeled with surveys of the sky, and that's how we're learning about dark energy. But there's more. We could also be using these intrinsic alignments of galaxies to learn some of these dark secrets of our universe. And I think it's a promising avenue and one that we hope to realize in the years to come. So I'll just conclude there and see if there are any questions. Thank you.
Yeah, thank you, Beda, for your wonderful and exciting lecture. So we have got few questions. If you allow, we can start our discussion session. The first question: can single black hole be observed by its lensing effect?
So black holes, well, in general, okay, so let me see. Yes, in principle you can. So on the scales about which I was talking for this particular research, we're not talking about single objects, but many objects, right? Now, in principle, if you wanted to observe a single black hole, you could observe it through gravitational lensing, and there are proposals to do that. This is a different regime, a regime that's called microlensing. It hasn't been done so far, but you could, in principle, detect black holes through this gravitational lensing effect. What would happen is that the object that is in the background would suddenly become visible through this gravitational lensing effect, and then you would say, there's something in between that I don't see, but is causing the lensing. And this could be a black hole, for example.
Thank you, madam. Thank you. We have another question. So, could observational of GL, gravitational lensing, or other image phenomena from system of two merging massive dense object of the gravitational waves caused by their merge be connected?
I'm sorry, could you repeat that? I couldn't
I
hear
think
very
you
well.
can also see, please come the StreamYard page. I have added the question in the screen.
Okay, let's see. Yes. Could observation of gravitational of other image phenomena from system of two merging dense objects on of gravitational waves? Okay. Yes. In principle, yes. So you could have gravitational lensing behind a system of merging objects. I'm not sure whether this has been explored, whether it's detectable or significant. It's an interesting question. What is proposed is that gravitational waves themselves could be lensed. So this is connected to the question that you're asking, and this has been proposed, and it's something that people are currently looking for.
Well, thank you. We have another question. So, just curious, can galaxy die, and what caused them to die, and what will be the process? Do different kinds of galaxies have a lifespan?
Right. So as I said, there are different types of galaxies in the universe. Some of them are older, some of them are younger. What determines the age of the galaxy is the age of the stars that live in a galaxy. As the gas runs out of a galaxy, then you start seeing older and older stars. So in principle, in general, there is enough gas to continue forming stars for a very long period of time, even if you're an elliptical galaxy that is very old. So they won't effectively die. You would have to wait for a very, very long time. So it's not like they die. But what does happen to them sometimes, which is more dramatic, is that they might merge with other objects or be stripped by other objects. So if they fall, or if they have a very big galaxy nearby, they can degrade, so they can the stars can separate and go to different objects. And effectively there, I guess you could say that they died.
Okay, madam. Thank you. We have another question. So, madam, how can we watch other galaxies in the other universe through gravitational lensing?
No, unfortunately, that's not possible. So we can only see the galaxies in our universe through gravitational lensing. So there's a part of the universe that we have access to, and that's unfortunately all we can observe. Other universes, I mean, there are proposals, but not through gravitational lensing.
Okay, thank you, madam. We have another question. So it is said cosmic voids can have few galaxies. In our galaxy, part of a cosmic void, and how can we know?
Yeah, so there are these structures called cosmic voids, so the regions where you have very little, very few galaxies. Um, uh, there are ways to know whether a galaxy is in a cosmic void. So there are different ways. So, for example, you can map the motions of galaxies nearby or on. That's one way. You can also look at a phenomenon called the Sunyaev-Seldovich effect that has to do with how light interacts with the gas that is in our surrounding, and how we observe this interaction. So by looking at this interaction, you can decide whether we live in a void or not. So far, we don't think that we live in a void. We're pretty average, I think.
Okay, ma'am, thank you. We have another question. So, can we identify and observe first stage of formation of a galaxy using a telescope? And how long will it take for a galaxy to complete form?
Okay, good question. The first stages of galaxy formation are very uncertain. There's a telescope that is coming up, I think probably next year. It's called the James Webb Telescope. So it's going, it's like the successor of Hubble, and it's going to observe the first stages of star formation in galaxies. So we don't know much about that epoch. You can observe it, and we will using this telescope. I think it will be really interesting. How long it takes for a galaxy to form, it depends a lot on the galaxy and the physical processes that the galaxy undergoes, but the time scales that you should have in mind are from millions to billions of years. So this is very long time scales.
Yeah, thank you, madam. There is another question. So, it is said galaxies differ galaxies. Galaxy grows by ingesting other star system. So, just curious, is there a limit number of a galaxy to differ, or galaxy can differ or collide to ultimate number of the galaxy? Can a galaxy collapse if it had differed a lot of galaxies?
Yes, indeed, so galaxies collide with each other and they devour each other. There's no limit to the number of galaxies that you can merge with. It depends a little bit on what you call a galaxy, right? Because sometimes an object might devour a lot of little objects, and if you call each of these a galaxy, then you have a lot of them. But in general, mergers between galaxies that are of the same size, so say, for example, our galaxy is expected to collide with Andromeda. These are very rare in the life of a galaxy, very, very rare. What's more common is that they might absorb small galaxies like our own has. And then, for example, our own we have evidence of a few different galaxies having been absorbed by the Milky Way. Can a galaxy collapse if it has devoured a lot of galaxies? No, not really. I mean, what happens is that it simply stabilizes in a new configuration that allows it to be gravitationally stable. Some matter will funnel to the black hole in the center and will be eaten up by that black hole, and that will drive some period of activity. Sometimes if you have two black holes in these merging systems, they will also collapse and merge with each other. But it's not like the whole galaxy will collapse.
Okay, madam. So, thank you. There is another question. So, is there a dying galaxy in our observable universe, and can we observe them using telescope?
So the closest thing to the dying galaxy are these galaxies that I mentioned, which are elliptical and they're red. And you can quantify how close to dying a galaxy is by looking at a color. So in that sense, yes, there are a lot of dying galaxies in our observable universe, but there's still always a little bit of star formation in them.
Okay, madam. Thank you. This may be the last question. So maybe you have already explained it, but still. So what will happen to Proxima Centauri, the nearest star, if Andromeda and Milky Way collides?
Right. So if Andromeda and the Milky Way collide, if you look at the actual density of matter in our galaxy and in Andromeda, you realize that it's actually very low. So what will happen when these two galaxies collide is that most matter will just pass through each other. It's not like head-on collisions between stars will almost certainly not happen. So I think Proxima Centauri is pretty safe. I don't think we will see many changes in our very local environment.
Thank you, madam. So thank you, madam, for your wonderful presentation and excellent discussion session. I think our students have learned a lot of things about the cosmology and the galaxy. So as we have seen the lot of questions, so they are very interesting. Feel interested in your topics. So thanks again for giving us this opportunity. Actually, it's a good opportunity for them to interact with you directly.
And
So
thank you very much for the questions and the invitation.
yeah. So after the COVID, I'll definitely invite you for a face-to-face session, and that will be great for our students. So thanks again, madam, for giving us this opportunity, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So bye for today. Have a nice day. Bye bye.